My name is Brooke Weefray, and today I'll be going over a problem on the titration of acetic acid with sodium hydroxide from Chapter 18, Aqueous Ionic Equilibrium. The problem reads, consider the titration of a 20 milliliter sample of 0.105 molar acetic acid with 0.125 molar sodium hydroxide. Determine the following. A, the initial pH, B, the volume of base required to reach the equivalence point, C, the pH after 5 milliliters of added base, D, the pH at the equivalence point, and E, the pH after adding 5 milliliters of titrant beyond the equivalence point. So let's quickly review what's occurring in this titration by looking at the equation. We have the analyte acetic acid reacting with the titrant, sodium hydroxide, to form water, and the salt, sodium acetate. And note that sodium is a spectator ion, so it will not affect the pH, and I'm going to omit it from the rest of the presentation. So the problem is asking us to find the pH as different quantities of sodium hydroxide are being added, and we expect the titration curve to make this S shape as it becomes more basic. And finally, let's review the given units. We have 20 milliliters of acetic acid at a molarity of 0.105, and we have 0.125 molar sodium hydroxide. So part A asks for the initial pH of the solution before any sodium hydroxide is added. So to do this, we just need to find the pH of the acetic acid solution in water, and since acetic acid is a weak base, we need to construct a Rice table. So here's our Rice table. We know that the concentration of acetic acid is 0.105 molar, so we can fill in the rest of the table with this information. Here's the Ka of acetic acid, which we use to write our equilibrium expression. And we can simplify this by using the x is small assumption. Then multiply both sides by 0.105, and finally take the square root of both sides and get x equals 0.0001359 molar, which is the concentration of hydrogen ions. To find the pH, we take the negative log of our hydrogen concentration, and this gives us our final answer, pH equals 2.868. And here's the check for our x is small assumption, which we see does in fact work. Part B asks for the volume of base required to reach the equivalence point. So to solve this problem, we can use the titration equation, which computes the molarity and volume at the equivalence point by setting the moles equal to each other. We are given M1, V1, and M2, so we can just plug these values in to solve for V2. But first, we need to convert the volume of acetic acid to liters, so we just divide by 1,000. Now we can plug in all of our known variables and solve for V2. First, multiply the values on the left-hand side, then divide by 0.125 molar to isolate V2. This gives us our volume in liters, which we need to convert back to milliliters by multiplying by 1,000. And here's our final answer, 16.8 milliliters. Part C asks for the pH at the point on the titration curve when 5 milliliters of sodium hydroxide have been added. So when sodium hydroxide is added, the pH changes because the concentrations of acetic acid and sodium hydroxide are changing as they react. So to find the pH, we have to find these new concentrations by seeing how many moles have reacted. Our first step is to find the mole quantities. We are given the volume in milliliters again, so we need to convert it to liters by dividing by 1,000. Now we can find the number of moles of sodium hydroxide by multiplying the volume by the molarity. We can do the same for acetic acid. Next, we plug these values into a mole table to see how the number of moles change. And here's our equation, excluding the sodium ions. And here's our mole table. All of the added OH reacts with acetic acid, so both of these quantities decrease by 0.000625. And since they form acetate, the quantity of acetate increases by 0.000625 moles. With these new quantities, we can use the Henderson-Hasselbalch equation to solve for pH. And even though it asks for the concentration of acid and base, we can just use moles here because they have the same volume, so they would just cancel out. So here's the Ka of acetic acid, and for pKa, we take the negative log of Ka, and then we can just plug the moles of acid and base and solve to get a pH of 5.38. So part D asks for the pH at the equivalence point, so we'll use the same approach, but we will need to take it one step further at the end. So first we find the mole quantities, and we know that at the equivalence point, the number of moles of acid and base are equal, so we have 0.0021 moles of each. Now we plug these values into our mole table to see the change in moles. And this is the same table as before, except we have a different value for the number of moles of hydroxide being added. Acetic acid and hydroxide react completely, so there are 0 moles left, and they form 0.021 moles of acetate. So now there's only acetate and water in solution, so to find the pH, we need to make a rice table because acetate is a weak base. For our rice table, we need the molarity of acetate. So we divide the number of moles by the total volume of the solution and get 0.05706 molar. Now for our rice table, we can just plug in the concentration of acetate and fill in the other parts of the table. We know the Ka of acetic acid, so we can use the equation Kw equals Ka times Kb to solve for the Kb of acetate. Now we can use the Kb to write our equilibrium expression, and we can simplify by using the x is small assumption, multiply both sides by 0.0506, and take the square root of both sides to get x, which is the concentration of hydroxide ions. We can now find the pOH by taking the negative log of the concentration of hydroxide ions, and this gives us a pOH of 5.244. Finally, we subtract the pOH from 14 to get pH, and get our final answer, pH equals 8.755. And finally, our last problem asks for the pH after adding 5 milliliters of titrant after the equivalence point. So we'll follow the same approach as the other pH problems by first finding the mole quantities, and we need to find how many moles are in this quantity of added base. We know from part B that at the equivalence point there is 16.8 milliliters of base, so we add 16.8 milliliters plus 5 milliliters to find the volume of added base. Now we multiply this volume by the molarity to find the number of moles of base, and we know from our previous step there is 0.0021 moles of acid. Now we use the same mole table, except with different quantities of added base. So here there is more added base than there is acid, so we are left with excess hydroxide and some conjugate base. And in this situation, the strong base overpowers the weak base and dictates the pH. But before we take the pOH, we need to find the concentration of hydroxide. So we divide the moles by the total volume of solution. We get 0.01495 molar. Now we can calculate the pOH by taking the negative log of this concentration. And finally, we find the pH by subtracting the pOH from 14. We get our final answer, 12.17. So that is all for this problem. To summarize, we found the pH at several points on the titration curve by following the same process of finding the mole quantities, calculating how these quantities changed, and then using different methods to find the pH from these quantities depending on the problem. And as we expected from the titration graph we looked at in the beginning, the pH increased with each addition of hydroxide. Thank you for watching.